Alright guys, so here is the key for the Chapter 6 practice, and just to warn you, I ran out of coffee, so I am very grumpy. Alright, so number one, if system releases 87 joules of heat and does 45.6 joules of work on the surroundings, what is the delta E for the system in joules? So, if we have E for the system, because we need E for the system, we need Q and W, because E equals Q plus W. So if we have 87 joules of heat and the system releases it, that means that is a negative term, and also 45.6 joules of work done on the surroundings, that means that is also a negative term, because work is negative if the system does work on the surroundings. So when you add those two together, you get negative 132.6 joules. That's number one. Number two, if E for the surroundings is positive 49 and the system releases 28.4 joules of energy, what's the value of W for the system in joules? There we got the same equation, E for the system, blah, blah, blah. This time it tells you E for the system and it tells you the releases that joules of energy. So yeah, you know those two terms and you don't know the work, so you solve for the work. And again, if E for the surroundings is positive 49.9 joules, then E for the system is negative 49.9. And if the system releases this much energy, it means Q for the system is also negative. So again, negative 21.5 joules is the work. Number three, a small amount of hydrogen and oxygen are allowed to react, and during the reaction, the surroundings absorb this much energy, meaning that is Q, and the container expands from 4 liters to 14 liters at a constant pressure of 1.3. What is delta E for the system for the reaction in joules? Remembering that 101.3 joules is 1 liter ATM. So again, we have Q is equal to, or E is equal to Q plus W, and then we have Q already, and we have to find W. So W is negative P delta V, so we have the pressure times the change in volume, and then we have to change that to joules by multiplying by the factor joules per liter ATM. So the liter in ATM on the bottom will cancel with the other liters over here, and there should actually be one more parentheses there. And when we multiply that and then change that to kilojoules, we got to move the decimal point 3 places for that product, and then add it to this. It's not a whole lot more. It is just negative 24.9 kilojoules for number 3. Number 4 asks us, if a sample of gas is allowed to expand at constant pressure of 1 atmosphere from 2 liters to 4 liters, what would be the work in joules? So for that first part, we have work is P times delta V, and we have the pressure in atmospheres and the change in liters, and then we change that into joules by using the conversion factor, 101.3 joules per liter ATM. I may or may not give you this factor on the test, but you can derive it by using the two values for R that you know. You'll be given these two values for R, 8.314 joules per mole Kelvin and 0.08206 liter ATM per mole Kelvin. And if you divide these two, the mole Kelvins cancel out and you're left with joules per liter ATM. Well, when you divide this by this, you wind up with 101.3. So you can derive this even if I don't give it to you. So I may or may not give it to you, I don't know. Depends on how I'm feeling, because unlucky for you guys, I'm going to revise your test after I do this, because I was going to revise it anyway, but now I'm in a foul mood, so yay, hopefully that doesn't change how I make your test. But it probably will, so whatever. All right, so there's no net change in energy from the gas. What will happen to the temperature of the sample? This is it's easiest just to look at this as a qualitative thing. So if the gas is expanding, then that must mean that the temperature is going up if the pressure is not changing. Because pressure, temperature, and volume are the only three things that really relate to each other. If it's a closed container, the moles aren't changing, and if the pressure isn't changing, if the temperature is going up, the volume must be going up too. Those are directly related. So you can just answer that qualitatively by remembering gas laws. So if volume goes up, temperature goes up. Number 5, what is the capacity of a substance that absorbs 472 joules of energy and goes from 23 to 87? We're just going to use Q equals C delta T. That is heat capacity, not Q equals SM delta T. That is specific heat capacity, or just most of the time called specific heat. So we substitute in for Q and for delta T, and we get a C of 7.28. So that's number 7. Number 8. Same thing, but now it asks what is the specific, oh sorry, that was number 5. Number 6, what is the heat capacity, what is the specific heat capacity of a 10 gram piece, the blah, 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 blah. So we substitute everything in there that we know. We know the joules and the mass and the delta T, and we solve for S, and we get S of 0.134 joules per gram degree C. Number 7, I drop a 15-gram piece of metal, blah, 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 calorimeter. So we define the metal as the system and the water as the surroundings. So we have Sm delta T for the metal is equal to negative Sm delta T for the water. And we know S and M and delta T for the metal, and we know S and M and delta T for the water, and we got a negative there, and when we substitute and simplify, we get an S of 7.63 joules per gram degree C, which is way higher than any metal should ever be, but whatever, it's just an example. Then number 8, it asks us to recalculate the specific heat capacity of the if the calorimeter, the heat capacity of the calorimeter is 6.8 joules per degree C. Here in the previous problem, it said assume no heat loss to the calorimeter. So this one, we have to put that back in. So luckily it's the same exact numbers, but this time we have to actually add in the term for the heat capacity of the calorimeter. So that's S. The surroundings this time are both the Q for the water and Q for the calorimeter. And since the calorimeter is an object, it's just C delta T, so still negative, and just those two. And that, when you work it out, is just a little bit higher, so 7.76 joules per gram degree C. All right, number 9, I burn 1.28 grams of acetylene in a bomb calorimeter. The temperature rises from this to that. The delta H for the reaction is, for the combustion of acetylene, is negative 1299.6 kilojoules per mole. What's the heat capacity of the bomb calorimeter? So in order to get heat capacity for the bomb calorimeter, we're going to use this equation, Q equals C times delta T, and we have the temperature change right now because we have the two temperatures, and we can find the Q. It doesn't give it to us directly, but it does give us the mass and the delta H. So we change the grams to moles for acetylene. That's just the grams per mole for C2H2, which is acetylene. And then we know the delta H, so we multiply and divide, and we get negative 63.88 kilojoules. Well, that's how much the acetylene released, which means that that's how much the calorimeter absorbed. So that's why this is a negative and that's a positive. And so then we solve for C for the calorimeter, and we get 15.4 kilojoules per degree C. All right, number 10 says, I used the same bomb calorimeter in the previous problem to find the heat of combustion for lactic acid, and it gives you a bunch of data. So in this one, we have C for the calorimeter, and we have the delta T, so we can find Q, and Q is 38.192 kilojoules, and that should have 3 sig figs, because each of these has 3 sig figs. So then we take, and for delta H, we need the kilojoules and the moles, so we just take the grams of lactic acid, and we convert to moles by using the molar mass, and we find the molar mass just by adding them all up. And we get 0.006460 moles, and that works up to 5912, and since it has 3 sig figs, it rounds to 5910 kilojoules per mole. So that's number 10. Number 11 says, use the following reactions to determine delta H for the reaction for that third reaction. So this is Hess's law. We need to combine these top two to give us that third one. Well, the second one and the third one are almost exactly the same, except we have H2O gas here and H2O liquid there, and 2 of each. So we need to use this top equation to make that gas go away and that liquid arrive. So to do that, we use the top equation as it is, and then we just use we use B as it is, and then we use A, that liquid going to a gas, but we have to first reverse it, so that positive 44 kilojoules becomes negative 44 kilojoules, and because we used it twice, we have 2 times negative 44 kilojoules. So when we add these two together, we get negative 890 for the sum of those two, and I'm just showing that these two cancel out because they are in the products and the reactants right there. Should not include the arrow, but whatever. All right, number 12, use the following 3 reactions to determine the delta H reaction for the fourth in kilojoules. So again, we add them together in such a way that they add up to the thing that we want. The way that I did it was I just said, okay, I want C2H2, so I'm going to use that reaction, and then I want 2 carbons, so I used 2 times that reaction, but I had, so I didn't have to reverse that one. I had to reverse that first one, so it's negative. And then I used that reaction, but twice, and then this one I used, I think, just as it was, but reversed as well. Yeah. There is an error in the thing here. Here we have carbon solid, and here we have carbon gas. This one should have still been carbon solid, because there's no other way that we can get that. So, you're welcome, Lindsay. Lindsay just texted me through Remind. All right. And there's the bell. Yay. So, it is 3 o'clock. All right, so number 13, we got the heats of formation to solve the following problems. So first one, In 13, when CH4 is burned indoors, the reaction produces carbon monoxide and water instead of carbon dioxide and water, because we're starving it of oxygen. It consumes the oxygen in the surrounding environment, and then it burns not as efficiently. Which reaction producing carbon dioxide or carbon dioxide produces more energy? So to do that, we first had to write the reactions for the two burnings of methane, one producing carbon dioxide, one producing carbon monoxide, and balance those reactions, and then use the heats of formation to figure out the delta H. Now, it's a little bit, the way the question is worded, it should have been more clear which reaction producing carbon dioxide or producing carbon dioxide produces more energy. You can just go with the straight numbers, because the straight numbers just say that 890 and 1214, that the second one produces more energy. But it does produce more energy, but for 2 moles of consumption of CH4. So a better way to ask that question, some friggin' moron wrote this apparently, would be which reaction produces more energy per mole of CH4 consumed? Because really this one, this top one, produces more energy per mole of CH4 consumed and is a more efficient reaction. This is a less efficient reaction. That's why it does not happen as often unless we are starving it of oxygen. Unless we're starving it of oxygen. We see the ratio between methane and oxygen here is 2 to 1, and here it is 3 to 2. So this is a smaller ratio, which means it uses less oxygen. So if it's in an oxygen-starved environment, it's more likely to have this as the reaction, which is a less efficient reaction because it releases less kilojoules per mole of CH4, but it's the necessary reaction if it's in an oxygen-starved environment, so whatever. So if it were on the test, I would have to word it better, because the correct answer here would be this first reaction, even though it looks like this second one produces more energy. All right, then for B, what is the delta H of formation for ethanol if the combustion of ethanol has a delta H reaction of negative 1367 kilojoules per mole? So we first have to write the combustion and balance the combustion, and then we know that it has the reaction has negative 1367 for the delta H, so we use everything here, and then we do the products, which are these, minus the reactants, and obviously oxygen is 0. So the only thing we don't know here is the delta H of formation for ethanol, and when we solve for that, we get negative 277.4. 277.4. So that's 13. In 14, we have 33.6 liters of CH4 combustion under a dish containing ice. The delta H for the combustion is blah, blah, blah. How much ice can you melt? How many grams of ice? If none of the heat is lost to the environment, which it always is, but let's assume it's not. So we start off with our conversion, and we have 33.6 liters. We convert liters to moles. I should really have told you that it was at STP, and because that's the only time you can use this 22.4 liters, to which a lot of you are like right now are like, wow, you didn't say it was at STP, that's why I couldn't do it. I mean, you just had no idea how to do it. Shut up. So we convert liters to moles, and then moles to kilojoules, and we get our kilojoules of 1203 kilojoules, and then we can convert that to grams by using the delta H of the reaction, because that needs 6.00 kilojoules per mole of water, and then since it asks grams, we put moles into grams, convert moles into grams, and we get 3,613, but it has 3 sig figs because the 33.6 has 3 sig figs, and also this does, and also that does, so it is rounded to 3,610 grams. And then number 15, in number 15, it asks, or it says, I leave 2 liters of 20 degrees C water on a hot plate and turn the hot plate on. I forget to turn it off when I leave for the day. The hot plate can transfer 6.8 kilojoules of energy per hour. How long will it take to boil away completely? And there's the S for water, and there's the delta H of vaporization in kilojoules per mole. So there are 2 steps here. First, the water, before it can boil, has to heat from 20 degrees Celsius to 100 degrees Celsius. So that's QA equals SM delta T. There's S and M. Since it's 2.0 liters, sorry, 2.00 liters of water, this should actually be right here, then it goes from 20 to 100, so that takes, just that step takes 669,440 joules, or if we change that to kilojoules, because we're going to have to later anyway, we got 669.440 kilojoules. Step 2 would be the actual boiling, so that is Q equals M delta H, because that is a phase change. So we got Q is equal to M times delta H. And the delta H we're given is in kilojoules per mole. So we have to use an additional factor here to convert moles to grams, because we have grams here. Or you could convert that to moles first and then just use the same number. Either way, it doesn't matter. So we got that, decimal point, and we got 4511.7 kilojoules, and we have to add those two steps together, so that plus that original kilojoules, and we get 5,181 kilojoules. And in order to figure out how much time it would take, we have to use the conversion, the 6.8 kilojoules per hour, and we find that it takes 762 hours, and this should actually only have 2 sig figs, so that should be 760 hours, which is a hugely long time, which, yeah, it's because hot plates can transfer way, way more than 6.8 kilojoules per hour. That's like maybe 6.8 per minute or even less. So water boils very fast on those. And that's it. That's number 15. Okay. So